Hello, everybody. Welcome to all. My name is Arni Rao from the Medical College of Georgia. Today, we all are happy to gather here to celebrate the birthday of Dr. C.R. Rao, 10 September 2024. And this is the first kind of series after he passing away. Unfortunately, last year, this is the first kind of series of talks that we are organizing. So all his friends, collaborators, family, students, everybody gathered today to celebrate his birthday. And I'm really honored to host the session. So before I uh, introduce the speaker, Professor Efron, I would like to show a couple of slides on Professor Rao. So Dr. Rao is popularly known as CRR in the US, and in India is known as Dr. Rao at ISI Kolkata. He was born in 1920 and passed away 2023, just a couple of weeks before the age of 103. And last 3-4 years since he celebrated his centenary year, a lot of attention on Dr. Rao's work all over the world. And several obituaries appeared, tributes appeared. For example, in 2023, after passing away, Science published an obituary written by David Banks and Jennifer Clark. And similarly, C.R. Rao, Paramount Statistical Scientist, obituary in PNAS by Anirban Dasgupta. C.R. Rao, statistician who transformed the data analytics by Teja and Khattree in Nature. And the survey statistician published the obituary, myself, Krishna Kumar, and Pramod Pathak. Pramod Pathak did PhD under Dr. Rao in 1950s, and he currently at Michigan State. And this article, we also wrote a very elementary way of, it's a technical article, but elementary proof of Kramer-Rao inequality and all the technicalities in elementary way. Students, the new students can refer to that article, the tribute there. And then Notices of American Math Society. They published a 15-page beautiful tribute during his 102nd, 101st birthday by George Andrews, number theorists, and many other mathematicians, statisticians combined together, 15 co-authors. They all published, that combined tribute published in Notice of American Math Society. And Significance wrote an editorial, A Life to Enlighten Us, Remembering C.R. Rao by Kathleen O'Grady. And C.R. Rao's Century Significance, the magazine Significance published, written by Efron, Amari, Rubin, myself, and David Cox. Many other things one can read on Dr. Rao. And his first article was published when he was 22-year-old. And before he went to do PhD under Ronald Fisher, Rao published almost 19 articles from India before he started his PhD work. And Kramer-Rao, the famous work, Kramer-Rao bounds, that famous work was his 14th article. So all that is described in all these tributes, various tributes. So now I take the opportunity to introduce our distinguished speaker, Professor Efron. The title of the talk is A Diagnostic Function for Bootstrap Confidence Intervals. Bradley Efron is a professor of statistics and biomedical data science at Stanford University. And Efron is best known in statistics for bootstrap techniques, information geometry methods, empirical Bayes. And he knew Dr. Rao, C.R. Rao, for several decades. And they have a great bonding. And he shared a lot of information in his previous talks on the association, all these things that is available in various YouTube channels and articles and tributes. And his work on, Dr. Efron's work on empirical Bayes, he popularized the empirical Bayes, and that is beautifully, Efron's work was beautifully summarized by Daniel Garcia and Alasdair Young in a recent article published in Journal of Indian Institute of Science in 2022, the title Empirical Bayes in Selective Inference, that beautifully summarized, his contributions on empirical Bayes. Of course, the bootstrap techniques today is going to speak, and information geometry methods he spoke during Rao's centenary. And selected awards of Professor Efron. 2019, he won the International Statistics Prize. 2014, Guy Medal in Gold. 2005, the US National Medal of Science. 2003, C.R. Rao and Bhargavi Prize. 1990, S.S. Wilkes Memorial Award. Popular books or textbooks or monographs by Efron. 2023, Exponential Families in Theory and Practice. 2016, Computer Age Statistical Inference, Algorithms, Evidence, and Data Science. 1993, Efron Shipsharani, An Introduction to the Bootstrap. 1982, The Jackknife, the Bootstrap, and other resampling plans. And he provided leadership to the various societies. For example, he was president of American Statistical Association in 2004. And 1987-88, he was president of IMS, Institute of Mathematical Statistics. And he was elected fellowships to various societies across the world in various countries. For example, he was a fellow of American Statistical Association, Institute of Mathematical Statistics, International Statistical Institute, American Association of Advancement of Science, and American Academy of Arts and Sciences. Thank you all. Let us now listen to Professor Efron.
Okay. Thank you, Arnie. And thanks to these inviters for inviting me at this 103rd birthday party, or maybe 104th. It depends if you count zero or not. Some people do. I'm going to share my screen now. This is going to take me a second to get this right. Okay. And now I'm going to go to full screen. And I hope everybody can see this. This weird picture in front is a modern art version of the columns that they have around Stanford. And it looks like a monster, but it actually is supposed to be art. So in 1965, when I was a brand new assistant professor, I can still remember how excited I was to get Professor Rao's book on linear statistical inference and its applications, a book which covers a lot more than linear models. And really, I took out my copy again before this talk, and it's covered with notes, marginal notes that I made, thinking about the many points, subtle points, I might add, that Professor Rao brought out. The uh, the the preface to the book ends by thanking two people, R.A. Fisher and Mahalanobis. And R.A. Fisher and Rao, you can't do better for statistical heroes. Um, this talk, I'm afraid, is more Fisher than Rao, but I'd like to think that Professor Rao would have liked at least the question raised, the problem raised in this talk, which is the problem of setting good approximate confidence intervals, even if you didn't particularly like my solution. So let's get going. So the standard intervals, we observe theta hat as an estimate of theta, some standard error sigma. Sigma usually has to be estimated, but here I'll assume we know it. We set an approximate 95% two-sided interval for theta, theta hat plus or minus 1.96 sigma. We claim that that's a 95% approximate confidence interval and will be exactly accurate and correct if we're in a normal translation family where theta hat is theta plus sigma z. Z is always going to stand for a normal 0, 1 in this talk. And the standard intervals are at least a century old, more than that actually, and they're immensely popular, and they're reasonably accurate, but a lot of times not so accurate, and that's part of what this talks about. Their main virtue is they're virtually automatic. You can write one computer program that does it all the time, and the user doesn't have to worry about which particular case he's using. And that's particularly true since you can estimate sigma by, say, the bootstrap. So here's a data set that I'll be using for illustration. It's from Mardia and Bibby. Actually, it goes back to Mardia, Kent, and Bibby. Mechanics and vectors. There's 22 students. I've chosen these from a set of 88 in Mardia and Bibby. Each row is one student. They've taken 5 tests. The first student didn't do very well in mechanics, did better in vectors. Then you see the scores across. So there's this data matrix X is 22 by 5. 22 students, 5 tests for each student. And the model in Marty and Bibby, X has independent rows, Xi normal 5 mu sigma. Mu is a 5-dimensional vector, sigma is a 5 by 5 data matrix. And I'll take for my example to start with parameter of interest, theta, the correlation between mechanics and vectors. That's the first 2 columns of the data matrix. That turns out to have MLE 0.496, just about 0.50 here. And sigma hat, according to an ancient formula, is 1 minus theta hat squared over the square root of n minus 3. N's 22. That's 0.173. And that gives a standard interval theta in 0.160 through 0.836. Well, here's in this problem, I chose this problem because it's a situation where you can get exact confidence interval. That's because it's a 1-parameter problem with no nuisance parameters. The exact interval, the lower end point is 0.093. That's the red curve. The red curve is the probability density of the correlation coefficient from a sample of size 22 if 0.093 is the true theta. And that's courtesy of Fisher, about one of his very first papers. The green curve at the other side, the upper endpoint is 0.751. And if the true parameter theta is 0.751, you get that green density function. The black density function is the maximum likelihood estimate of the density if theta is 0.498. And what you can see right away is you're not in a normal translation family. It's anything but that. So Fisher, one of his next papers, the wonderful transformation trick, Fisher said, well, the standard method isn't going to work very well on this problem with theta and theta hat. I'll change to phi equals m of theta and phi hat equals m of theta hat, where m of theta is this peculiar transformation, Fisher's Z transformation, 1/2 log of 1 plus theta over 1 minus theta. And he says that'll put the problem more into, he had reasons to say this will make the problem after you make this transformation, approximately phi hat will follow a normal translation model, normal phi sigma squared. And you can apply the standard method on the phi scale, and it's going to work well. And then you can do the inverse transformation back to the theta scale. That's at the bottom line there. So that's awfully clever, right, if it works. Does that really make for a normal transformation? Here's those three curves now on the Fisher Z scale. And look at it, really looks like you've got a normal translation model. So here's the exact and approximate endpoints for that problem I had. We have 22 samples, and we have the true correlation. We have the observed correlation is 0.498. The standard interval, as I said, is 0.160 through 0.836. Fisher's method gives 0.097 through 0.760 as the correct 95% interval. That means there's 2.5% error on the left and 2.5% error on the right, nominally. The exact interval, which exactly does that, is 0.093, 0.751. So Fisher isn't far off. And the BCA method, that's the bootstrap method I'm going to talk about, is about the same accuracy as the Fisher method, 0.086, 0.754. So that's a method that uses a lot of bootstrapping. So we're going to talk about that. So why don't I just always use Fisher's method? Well, there's two things wrong with Fisher's method. The first thing is it requires Fisher. If you have another problem, a different one than the normal correlation coefficient, you have to think of a new method. Maybe there isn't one. But the bigger objection is that Fisher's method doesn't include nuisance parameters. The reason I chose the normal correlation problem to start with is in that problem, theta hat only depends on theta, even though there's lots of nuisance parameters. BCA stands for bias corrected and accelerated. It's a method I've been trying to get people to use for a long time. It's a bootstrap algorithm that gives more accurate approximate confidence intervals, and it has a lot of virtues. It is automatable, and it doesn't require a Fisher, and it does allow for nuisance parameters. So I'll give an example of having nuisance parameters. The same data set, student score matrix X, assuming the rows are independent 5-dimensional normals, and now let theta be the maximum eigenvalue of sigma instead of the correlation. So theta hat, the maximum eigenvalue of sigma hat, I calculated it as 683. How accurate is that? We want a confidence interval. Now, normal 5 mu sigma, it turns out to be a 20 parameter family. I'll tell you that later. So there are 19 nuisance parameters in some sense. And we're going to get around that by doing parametric bootstrapping. xi star normal 5 mu hat sigma hat. Mu hat's the usual MLE for the mean, sigma hat's the usual MLE for the sigma. Uh, we get both of those from X. We sample 22 times independently, and those are the rows of the bootstrap data matrix X star right at the bottom there. That gives us sigma hat star and gives us theta hat star. And I did 8,000 of those. I didn't need to do 8,000. I could have stopped a lot sooner. Uh, that's the histogram of the 8,000 theta hat stars, the maximum eigenvalue stars. And the histogram isn't as bad as the correlation coefficient ones were, but it's pretty non-normal. It's got a long tail to the right. And you could guess that for this problem, probably the standard method isn't going to work very well. The black arrows indicate the 95% confidence interval for the standard method. The red arrow indicates uh, the 95% interval for the BCA method, which is much longer to the right and much shorter to the left. And I'm going to try and what this talk is about is to say how we get the red arrows and then how dependable is the calculation that gives them. And there's some good things about the BCA intervals now that I'm selling that here. They are automatable in the sense that you can write one program that handles all cases. And that's particularly true for the non-parametric version of this, which I'll get to near the end, which is actually the most useful. They're transformation invariant. I'm going to use notation like theta hat square bracket alpha for the BCA alpha level endpoint for theta hat in any particular BCA interval. If phi equals m of theta and phi hat, then phi hat square brackets alpha is m of theta hat of alpha. That is, the BCA methods transform correctly, so you're never on the wrong scale. The reason the Fisher's method works so well is it puts the standard method on the right, correct normal scale. You don't have to worry about that with BCA. That's why you can write one program that does it all. The BCA method is second order accurate. The actual coverage approaches the nominal level at rate what errors of order 1 over n instead of compared to 1 over n to the square root of n, which is a big difference. And a final point, this is very Fisherian and Raoish too. The method is correct. Theta hat alpha is correct as well as alpha is accurate. And what does that mean? It's hard to define correctness, but it's easy to define incorrectness. If I took my 22 data students and I randomly chose 11 of them and then did the exact interval, that would be exactly accurate, but it wouldn't be correct. It would be too wide. And correctness is a logical kind of statement that we'll say more about. Okay, so where do the BCA intervals come from, or moreover, what justifies them? And that's where we get to the normal scale transformation families, NSTF. This is a generalization of a normal translation family that allows a wider set of assumptions, and you can still get an exact answer. So it says a one parameter of CDFs, Fs of theta hat. And incidentally, I'm only going to talk about one parameter problems for a long time until I get to near the end when we'll go to the useful thing where we actually have nuisance parameters. Anyway, a one parameter family of CDFs, I've called it Fs of theta hat, is NSTF. If for some monotone transformation, phi equals m of theta and phi hat equals m of theta hat, we have that phi hat, and that's in the blue there on the second line. Phi hat is phi plus sigma phi times z minus z naught, where sigma phi, z is a standard normal. Sigma phi is 1 plus a naught phi. Uh, Here in this one, z naught corrects for bias, a naught corrects for acceleration. That is, the standard error not being constant as it is in the normal, as in the standard method. And Fisher's use is an example of NSTF, or what he thought was, he assumed was NSTF, where A naught and Z naught are zero, and M of theta is the Fisher Z transformation, 1/2 log of 1 plus theta over 1 minus theta. So the NSTF families are generalization of normal translation families that allow for a monotone transformation, a bias, and an acceleration. And so they went. You can make up families, but you have to know what's the right confidence interval in those families, and that's what the BCA is based on. If f sub theta of theta hat is NSTF, then you can write down a formula for what's exactly and correctly the one-sided level alpha confidence limit. It's the blue curve formula there. Theta hat of alpha is f sub theta hat inverse the distribution under the maximum likelihood of phi of z naught plus z naught plus z alpha over 1 minus a naught z naught plus z alpha. And that looks sort of ugly, I think, the first time you see it, but it's logically correct. That is, NSTF family, that's the exact answer. This just extends. If A naught and Z naught are zero and F is normal, then you get back the standard method. And there's one very good point about the formula. You don't need to know the transformation M. So that raises the question, okay, if we assume we're in an NSTF, we can use the BCA method to get exact intervals. How can we tell whether our family is an NSTF? And that's where the diagnostic function mentioned in my title for the talk comes in. So I'm just going to define the diagnostic function. Yeah, but knowing the definition isn't very important for this talk, but I thought I'd better say it. So for a given value of z, let alpha be phi of z. Phi is the standard normal CDF. So if z is 1.96, alpha is 0.975. Then let theta hat of alpha be the alpha quantile, and f dot theta of theta hat be the derivative of f sub theta of theta hat with respect to theta. This is a quantity that comes up in Fisher's fiducial theory also. And then the diagnostic function is in blue there. It's the ratio of f dot of theta at theta hat alpha compared to its value at the median, theta hat 0.5, divided by phi of z over phi naught, where phi is the standard normal density. And then at the bottom of this page is a theorem that seems to wrap things up. F sub theta hat is an NSTF if only d sub theta of z is linear in z. So it seems like we're home free. All I have to do to see whether I have a particular example. Do I think it's NST that the BCA method applies? I do the diagnostic function. If it's linear, then it applies. If it's not, it's not. Well, we'll see that's overly simplistic. A couple examples. The gamma scale family, theta hat is theta times a gamma with new degrees of freedom. New some fixed number like 10, 25. And here's the diagnostic function. The black curve, and it is a curve, it just looks straight, is the diagnostic function for a scale parameter gamma scale if nu is 5. And the dotted line, the dashed line is exact linear. So you can see it's pretty linear. At 10, that's the red curve, nu equals 10. It gets more flat. At 20, it's almost perfect. At infinity, it's exactly perfect. That's the straight line, the x-axis essentially. The z-axis, I guess I should call it, uh, is the case of a normal translation family, the case handled by the standard method. Okay, that looks good. Uh, here's so we might assume that we're doing pretty well with the NS with BCA if we're in this kind of family. What about the student T translation family? Now we'll take a one parameter family where theta hat is theta plus W, where W is the student's T distribution with new degrees of freedom. So if I let nu be infinity, then a theta hat is theta plus Z. We're back in a normal translation family. Otherwise, we're not. And I got a real shock the first time I did this calculation. I did the diagnostic function, and here they are. For nu equals 5, it's that black parabola. Doesn't look linear at all. For nu equals 10, it's the red dashed curve, 20 dotted, 40 dashed, 80 is teal green. It's starting to look pretty flat. If I go up to nu equals infinity, I'm back to normal translation family. That's the flat line. But that it looks like maybe the NSTF method, the BCA method, won't work well in student in these kind of models. Well, it does actually work pretty well. So there's more to say about the story. Okay, one more example of the diagnostic function, and this is the one I brought up at the beginning of the talk. The xi normal 5 mu sigma, theta the correlation between x1 and x2, the student core, theta hat the Pearson correlation coefficient, the mammal-E. And next, here's the diagnostic function for that exact situation with theta equals 0.498. And it's the red curve here. And what you can see is it looks very much like a student T translation situation. The degrees of freedom are about 63. So Fisher was very close to being exactly right when he made that transformation, but he wasn't exact. That is, he assumed that the degrees of freedom were infinite. And I say they're actually closer to a translation model. You can transform to a translation model that has about 63 degrees of freedom. Well, a translation model with a T with 63 degrees of freedom isn't very much different than a standard normal one, but it's a little different. And that's why Fisher's method wasn't exact in that problem. It's close though. Okay, so uh, we have a diagnostic function, and if things are perfectly linear, we're set. But what if they're not perfectly linear? What are we going to do? How can we interpret the diagnostic function to see whether things are working or the BCA method is working or not? Well, a GSTF is a general scale transformation. This is a bigger family still, which includes NSTF. But the idea is if we're in GSTF and we're not near NSTF, you're going to be pretty sure that the BCA method's not going to be working well. And that's what I'm going to be getting at in these next few slides. So at the top line there, I'm just reminding you what NSTF is, and it involves, after you make this wonderful transformation that you don't have to know, phi hat equals phi plus 1 plus a naught phi times z minus z naught. The thing to focus on there is that z, which is normal 0, 1. In a GSTF, we get to replace z with a function with a more general error function, W equals W little w z, um, where W little w is 0 is 0 and W prime of 0 is 1. That's for identifiability. Um, so a GSTF has one more big degree of freedom from an NSTF. It allows you to make the basic error function, instead of normal, some function of that some other distribution. So, for example, we could take W student new, in which case W little w of z would be T sub nu inverse. That's the CDF, the T CDF of new degrees times phi of z. Uh, with 63 degrees of freedom like we had before, it'll look very much like WZ is Z, but won't be exactly. And here's a key point. What is the diagnostic function for GSTF? Theorem, if f sub theta hat is a GSTF, then the diagnostic function is of the form 1 plus WZ times that acceleration constant A naught over W prime of Z. W prime of Z is a derivative. For an NSTF, W of Z is Z, W prime of Z is 1, and for every value of theta, d sub theta of Z is 1 plus Z A naught. So not only is it linear, the slope is that acceleration. Um, and the fact is that GSTF wouldn't be of any use if I couldn't get what the right confidence intervals are in a GSTF. But it is easy to get them. For any choice of W, there's a version of the BCA limits that's accurate and correct for that GSTF. And the idea of trying to see how nonlinear the diagnostic function is instead use that diagnostic theorem, the thing in pink there, to estimate W of Z, and then see if the GSTF limits for that W are much different than the NSTF BCA limits. If they are much different, then you have a good reason for doubting BCA. If they're not much different, then your BCA is on good footing. Okay, and now finally, all of this that's been going on for the last half hour has to do with one parameter families, but that's not where we want to be. We want to talk about families with nuisance parameters, and for that purpose, I'm going to take the data to be from multi-parameter exponential families, my favorite thing in the world. That is where the densities f sub eta of x are proportional to e to the eta prime y, where eta and y are p-dimensional vectors. Y is the sufficiency vector, and eta is the natural parameter vector. Usually we prefer to work with mu equals expected value of under eta of y, the expectation parameter vector. And then that has the nice property that if theta is expressed as some function t of mu, then theta hat is some function. It is a t of y, the MLE. And so there's going to be p minus 1 nuisance parameters. And so well, we're still stuck in p dimensions. How do we get rid of the p minus 1 nuisance parameters? Well, this is an idea of Charles Stein, another hero, almost actually a exact contemporary of C.R. Rao. Stein said we can, in some problems, we can replace the p parameter f sub eta of x with a one parameter approximating family where the family f sub hat lambda of x is f of eta hat plus lambda t dot of x, where eta hat's the MLE of eta, and t dot's the gradient of that vector t of mu at mu equals y. And you take those both those things, you take the data, you fix those things being fixed, you assume they're fixed, and then you have a one parameter family that only depends on the parameter lambda. And now we're back to a one parameter model, and we can apply the BCA formula and the diagnostic function. So example, the student score problem. I don't know why I said the maximum eigenvalue. I could have said correlation just as well. The data X, if you remember, has independent five-dimensional normal uh, uh, rows. And we have 22 of them. Then Y turns out to be 20-dimensional X bar 1, X bar 2, X bar 5. Those are the five row column means. X1 squared bar squared is the column mean squared. Five of those and 10 correlation cross covariance averages. That's 20 parameters. Theta, the maximum eigenvalue of sigma, has MLE theta hat max eigen of the empirical covariance of X. Or I could have just said for the correlation is the MLE is theta hat, the maximum likely correlation. Um, and now none of this would be of particular use if you couldn't compute it easily. And Naris and I have been working on crayon package. BCA boot uses the parametric bootstrap. You start with eta hat, the MLE of eta. You generate some bootstrap X stars. Each one gives a Y star and a theta hat star. And then the program BCA bar computes the NSTF BCA confidence limits. And it also gives the diagnostic function, and it gives a way of seeing if its nonlinearity is worrisome. And that involves getting the diagnostic function. And I won't say this in detail here, but the diagnostic function is easy to get in through the BCA boot. It's not a difficult calculation. It comes out automatically. It barely adds to the amount. Most of the calculation involves getting the bootstrap applications of theta hat star. Everything else is second order. So here's the I applied BCA boot to the student score data with correlation statistic as theta hat, and I got an estimated diagnostic function, and you can see that it looks pretty much like it did. That's just about like it did for the actual diagnostic function, which I showed you earlier in red. It's actually, yeah, it's just about the same. Here's the diagnostic function for the student score maximum eigenvalue. This one's really quite linear, as it should be, because we think so. So remember, I said I was going to try and convince you that the maximum BCA interval for the maximum eigenvalue was probably correct, and this diagnostic function backs it up. Here, how does it back it up? Well, the BCA boot also now includes a something that to test NSTF. Here's the typical kind of table it gives. You get for each alpha 0.025, 0.05, 0.95, 0.975. You get a theta hat square brackets alpha, the nominal BCA endpoint. And now you can ask, what would that, if you're actually in GSTF that has estimated by the program through that W function, what would that endpoint, what would be the point, the alpha? And if it's much different, then the NSTF alpha, you have reason to doubt BCA. In this case, it's nearly the same. The GSTF is about 0.024, 0.025, etc. So again, we're on good grounds for the maximum eigenvalue problem. Also for the correlation too. Um, the all of this has been parametric. Actually, as I started at the beginning to say, non-parametric is probably the more useful for ordinary usage. Bootstrap, if X is the data matrix, like our 22 by 5, a bootstrap application chooses 22 of the rows at random from X and makes an X star, gives a theta hat star, and then the function BCA non uh, 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 gives the BCA confidence limits. All the user has to specify the data matrix, of course, and the function like correlation or maximum eigenvalue. And here's what I got for the correlation. I did 8,000 of them. Here's the non-parametric diagnostic function. Once again, the degrees of freedom now are, looks like a student T again, degrees of freedom about 40 rather than 60, but very much in the same mode. One last slide. This is the most schematic of ideas, but I'll say it anyway. I, trying to say, what is this about correctness, and how does it fit in with asymptotics, traditional asymptotics? So this is really hand wavy stuff, but I'll wave my hands. We have a situation, we have the truth is out there someplace. That's that green dot at the upper left. That's the truth means we know what family we're trying to get a confidence interval for. We know just how we'd form the confidence interval. That's a rare situation. Um, Instead, what we statisticians usually do is assume some sort of class of models like the standard model and find out logically what kind of confidence interval would be correct if that model applied, and then apply that. And that's the standard point is just a point here because it's a small set. A bigger set is NSTF, and the NSTF, the BCA formula tells logically what's the correct way to get the answer. And logically, truth has to be closer to NSTF than it is to the standard method. And that's held up because that's why you get a second order accuracy instead of first order accuracy. Still bigger is the GSTF. And you might say, well, why don't I just go and always get the GSTF intervals? And won't they be better? Well, they might be theoretically better, but you have a lot of estimation to do. And I actually don't know how to automate the GSTF. Naris and I know how to automate NSTF. So that's the end of the talk. Let me again say my best wishes to the Rao family and to everyone, and thank you again, Arni.
Yeah.
I'll quit
Thanks a lot.
sharing.
Yeah. Thanks a lot, Professor Efron, for a wonderful talk, for delivering a very, very clear and easy to understand for all. So we appreciate your time. Before we go for question and answers, I would like to invite Professor Rao's, C.R. Rao's daughter, Dr. Teja Rao. Professor Rao was very, very lucky to have a great family support. They're all supporting, I mean, they're all very cheerful, and they all took care of Professor Rao so well. I visited Professor Rao several times because we both collaborated for the last 10 years for the Handbook of Statistics. I met him several times. First time I met in ISI Kolkata. Several times I met in Kolkata. Then I met here. He was always in a happy, cheerful mood. He is always respectful for all. And he was really lucky to have a great family. I invite Dr. Teja Rao, his daughter, to say a few words. Dr. Efron, you can stop sharing.
I'm trying to figure out how to stop sharing.
Okay. There is a red button.
Let me try again.
It's okay.
I'm not good at this kind of thing. Here's share. No, wait a second. Sorry, I'm having. I somehow got myself into a thing where I can't. Yeah, I can't see how to quit sharing. Oh, I see now. Sorry about that.
No problem.
Now I stopped sharing.
Yes. So, Dr. Teja Rao, you want to say a few words? She was here during the talk. Or I invite Mr. Veera Rao, his son, Mr. Veerendra Rao.
So Arni, the
Yeah,
Tejas thing is
here.
owner's iPhone.
Oh, owner's iPhone. Okay, great. Yeah, I will.
Yeah, if you unmute her, yeah. Tejka, you're on.
Hello, I'm on.
Yeah.
Hello.
Yeah, Dr. Teja Rao, please.
Hi, I'm so glad I was able to join. This has been wonderful. Professor Efron, thank you so much for doing the presentation today. You know, Dad would have been absolutely thrilled. Thank you so much.
No,
And
thank you. Thank you.
It was lovely meeting you so many years ago, and we all miss Dad. And I guess I want to wish him a very, very, very happy birthday wherever he is. And Arni, thank you for taking the initiative and putting this whole thing together. And we really appreciate it to take so much interest and show so much love and respect towards him. And I was also so thrilled to see so many people attending it. Thank you all very much. And you don't know how much this means to us. We miss him every day. And it's so nice to know there are people who appreciate and love him. Thank you all very much.
Thank you. Thank you, Dr. Teja.
Yeah.
Mr. Veera Rao.
Veera?
Yeah. Yeah, I think my sister said it all. We're very touched for being able to attend this event on his actual birthday. And Arni, thanks a lot for arranging a lecture series in honor of his birthday. And Professor Efron, I wish Dad was here. He'd have really be delighted to, hear this being in the area of Fisher. So we really appreciate this, and it's nice to see a lot of names that I recognize here on the Zoom call.
Yeah,
Very
lovely.
touched. Yeah.
It's just been beautiful. And I also wanted to share with you all, they opened a bust of my father, a bronze bust of him at the Institute in Hyderabad. And they did it for his 104th birthday. So a lot of beautiful things happening, and that fills our heart. And I think he's always with us. And so is my mom. Namaste, and thank you all very much. Take care of yourself, Professor Efron, and hope to see you.
Well, I hope so too.
Yeah.
Thank you.
Bye. Bye.
Yeah, thank you for Mr. Veera Rao also. Yeah, now the floor is open for question answers, questions and the comments. if any. Either one can type in the chat box or one can directly ask question and I can unmute. I think we can unmute all.
I might say that I know this talk was had a lot of twists and turns. It's quite a theoretical talk, more theoretical than I like to be. The paper is makes a lot of the points I elated over clearer. I hope so. It's on my website.
Yes. Any questions? So I have one question, Dr. Efron. Myself and my former student, Dr. Tejin Lee, who is my now current colleague in my university, we both discussed your article thoroughly. We tried to understand. In fact, he understood better than me your article. Here, as you rightly mentioned, the last figure, what you showed in the circles, NSTF, GSTF, and the truth.
Yeah.
Sampling plays a bigger role in getting the GSTF, NSTF, but we can never get the truth, as you rightly mentioned. So, and you mentioned the truth here. You mean by the true families, which the data belongs.
Yeah, I guess I had in mind that was the problem with schematic drawings. You may, once you start pushing them, you realize you haven't said what's really important. The truth, if it turned out that we were in a perfect normal translation family, then the truth would be that you could use the standard method and get perfect accuracy. If the truth was that you were in the NSTF, but not in a normal translation family, then BCA would do it. If the truth was you were in a GSTF, but not NSTF, then the more elaborate method would do it. And but that green point, of course, no real problem is going to be exactly like any of those. But the asymptotics tell you how close you're getting. And the asymptotics the asymptotics for the standard method go back 150 years or something, and you have a pretty good idea uh, what might go wrong. The asymptotics for the BCA go back to people like uh, Peter Hall and others who worked, David Friedman, Peter Bickel, worked out that the method is actually second order accurate, which is an important point. But of course, asymptotics don't do it, don't help much when you have a given data set. And one of the nice things about current statistics is that computer allows us to actually do calculations that apply to the given data set with some hope that you're actually seeing how well things work. And that's what the spirit of this talk was, that if you do the diagnostic function for a specific application of BCA method, you get a chance to see quite realistically whether it's in a good situation for being accurate. Of course, with random things, you're never sure you're accurate, but at least you can see whether the situation fits the model you're using.
Okay. Thank you. Thank you for clarifying.
Arni, I think Vinod had some question on, so if you can unmute him.
Yes, I can. I just unmuted him.
Vinod, you had a question about the generalized. I think he said something in the chat.
Yeah, I just unmuted him.
Yeah, I think he sent a message in the chat related to, you can probably.
Okay. Dr. Efron, Vinod.
Yeah.
Vinod says that the comment he typed there, he says that Tarald Sen has generalized Fisher Z transform. Would that modify your derivations?
First of all, the Fisher Z transformation is one of those mysterious, wonderful things that Fisher did. And yes, making it better, it'd be nice. I didn't know about that work. Making it better would enable you to look at specific cases more generally. However, the whole point of the BCA method is you don't have to know how to do it. That M of theta doesn't enter into the actual calculation. Well, how can that be? Well, it happens because the methods are transformation invariant. So you can just work with order statistics and things like that that don't depend on what the transformation is, and the BCA method is transformation invariant. So in a sense, I don't I had a big advantage over Fisher in that I have a big computer that does the BCA method, and I don't have to know what's the right transformation is. In problems like the maximum eigenvalue problem, is there even a transformation? Probably not. That makes the problem perfect. Uh, uh, but that's the kind of thing when you're doing day-to-day statistics. I know this talk seemed very theoretical at points, but actually it's all supposed to help in applications. You get the program like BCA non, and it's easy to apply. You don't have to think about the specifics of the problem, and uh, that's that's a big advantage that applied statisticians have now.
Thank you. Thank you. Are there any other questions? Krishna Kumar, he says that thanks, Professor Efron, for honoring Dr. Rao with your talk.
Good. It was fun to honor Professor Rao. He's an easy guy to honor.
Thank you. Yeah, there are so many comments are there.
I think we have one more from Shantanu Ghosh.
Where? Can we get a copy of the slides of today's lecture? Yes. So that this entire talk will be, I mean, the article is available online. I shared with all the people, all the audience.
Did I give you a copy, Arnie?
The
I'll be
slide?
glad to. Yeah, the slides.
No, you did not send me the copy. Maybe you can share the copy.
Yeah, I'll be glad to send them.
Thank you. And also the talk will be available in YouTube, Information Geometry channel. And we have another question after that by Santu Ghosh. Bootstrap is one of the great inventions in statistics. How is it helpful? How is it Bootstrap helpful in high dimensional analysis?
Well, the So that's a very good question. In theory, bootstrap doesn't depend on the dimension. In fact, the bootstrap is close to a maximum likelihood kind of method, and you start running into problems in maximum likelihood when you get in higher dimensions. And most of those problems have to do with bias. You start getting very highly biased estimates. The bootstrap amounts to a plug-in estimate, uh, and plug-in estimates start failing when you get in high dimensions. So methods like the BCA do tricks to get around that. And one of those tricks, for example, is estimating Z naught, the bias correction constant, which is easy to estimate in high dimensions. And what I didn't say is that if Z naught is very big, probably the method isn't going to work very well either. Z naught should be like 0.1 or minus 0.1 or something, or minus 0.2 or something. If in high dimensional problems, you may get to see right away that there's something wrong with the plug-in method, and one of those tests is whether Z naught stays reasonably small. This all has to do with something having to do with the curvature of statistics in higher dimensions. The kind of thing that you were talking about the information sciences.
Thank you. Thank you, Dr. Efron.
Can I advertise my own book on the new book on exponential families? The fifth, the last part has to do with BCA intervals and things like that. It goes into it in detail.
Yeah, please.
That's it. Please buy it. I need you to sell them.
I did show in the introduction, in your introduction, I did show that book in 2020.
Excuse me?
I did show that book in the introduction.
I know I did. I like that. Thank you. I've read several books, but that one's my favorite somehow.
Thank you. Yeah. Now I invite, if there are no more questions, I don't see any questions did I miss anything in the chat? Yeah. So I want to invite Professor Ravi Khattree, who is a distinguished professor of applied statistics from Oakland University, to say a vote of thanks. Ravi.
Thank you, Arni. Well, thank you, Professor Efron, for this illuminating talk on the diagnostic functions, where you have also provided some insight to what Fisher did or did not. Today is Professor Rao, C.R. Rao's birthday, and your talk is perhaps the best way to honor his legacy. As little or as much I knew Professor Rao as his PhD student, I surely know that among many innovative ideas he introduced, he took special pride in the method of scoring, score function, score test, as well as his work on second-order asymptotics. And I did read your paper, and that paper does use all those ideas. Okay. Also, he viewed bootstrap as one of the most innovative ideas and had a lot of respect for you for introducing that idea. Thus, it is very appropriate that your talk addressed all these ideas so succinctly and so eloquently. Thank you again, Professor Efron, for giving us an opportunity to learn these deep ideas directly from you. Thank you again.
Oh, thank you very much.
You are muted, Arni.
Yeah, thank you, Professor Khattree, for saying nice things. And also thank you all for joining the event. and to celebrate the Professor Rao's 104th birthday. So thank you, Professor Efron, and thank you all. And this particular talk will be available in the YouTube channel Information Geometry within a day. Thank you. Have a good day. Bye all.